Hello everyone, welcome to this online course on manufacturing processes. I am Kishore, Assistant Professor in the Department of Mechanical Engineering, MLR Institute of Technology, Hyderabad. As we are discussing metal forming, so in metal forming also we are discussing bulk deformation. So far we have discussed everything related to the extrusion, related to the forging, all the details. Also we saw, took some numerical based on that and we have solved. Now we are taking the second bulk deformation process, that is extrusion. So in today's lecture what we discuss about the extrusion, what this extrusion process is, and then we'll discuss about the mechanism and types of extrusion processes, and most probably we'll take one or two extrusion process in this lecture itself, and we'll try to discuss whatever the technicalities are there, whatever the mechanism over there, and then we'll end this and next lecture, that rolling we are going to take, and the last of this metal forming bulk deformation processes. So in today's lecture we'll discuss what extrusion is all about, what is this process is, then we'll see the two types of extrusion, main these two types of other processes are also there, but mainly these two types are there: direct extrusion and indirect extrusion. And based on that we'll take few numerical and we'll solve that numerical also in this lecture. So we'll start with this extrusion. What is extrusion? First of all, what is the meaning of extrusion? So extrusion, we already know in metal forming, all the metal forming processes. It doesn't matter what the process is. What is the basic fundamental? The basic fundamental is we are applying different kind of forces, and just because of that force, we are deforming the material. Means whatever the shape or the size we want in that particular specimen, just applying the force, we are going to get that particular shape. So what will happen? Either we are doing at the room temperature, or we are doing at a temperature which is generally known as hot working. That temperature is beyond the recrystallization temperature of the material, that which is generally being taken as half of the melting temperature of the material. Okay, so here also what we will do, we have to do, our specimen will be there, like our workpiece will be there. We can see here, suppose this is my workpiece, this green is looking, this is my workpiece. So what is happening here is the die, from both sides we have the die. Okay, or you can say container is there, and now our workpiece is inside. This is actually a dummy block provided. We discuss why these dummy blocks are provided, and this is the part through which you are applying the force. What is happening? This workpiece is inside this one, and we are applying the force from the back side. Means we are pushing it, and what is happening at the end? This die opening is provided. This is the die opening. This is the die opening. So whatever the shape or whatever the dimension of this die opening is, once we are pushing the workpiece from the back side, so we know it will flow over there, and once it will flow, it will start to move, and finally when it will come out, it will take the shape of this one. So you can see here, initially this was the diameter, or this was the thickness of the material, or the diameter of the material, but once it start flow and coming out from the hole or this opening of the die, it is taking the shape of this one. This is the final dimension. So here also what is happening, we are pushing or simply applying the force, and material is flowing inside that container where we have kept, and at the out of that there is a die which is having opening, and it has a particular shape, a particular dimension provided, so that once material will flow through this one, finally it will take the shape of that one. So this is also a plastic deformation process, means the severe deformation process. So extrusion is a bulk deforming process in which work metal is forced or compressed to flow through a die opening. Here we can see we are forcing it to pass through and produce a desired cross-sectional shape. Best example of this one is toothpaste. Every morning after getting up, what we are doing, we have to clean our teeth. So what we are doing, we'll have a toothpaste box. So in that toothpaste is there. What we are doing, we are simply pressing at a point, and because of that, we know from the Pascal's law, this whatever the forces we are applying, that will be transmitted. So because of that, that toothpaste is coming out from the opening provided in that toothpaste box. Similarly, here what is happening? The material is inside the box, and then from the back side we are applying the force, and at the end, through a die opening is provided. So what is happening? This material is flowing inside that, and once it is coming out from the die, it is taking the shape of that die opening, or whatever the shape is given to that die opening, it is taking, and finally our desired shape material or the workpiece we are going to get. Okay, so best example of this one is toothpaste. So what is the advantage of this one? A lot of different kind of shape can be generated by this process. Different kind of shape we can generate by this process. Okay, another thing is, as grain will be refined once the material will deform through this one. So if it will be refined, no need to tell, almost all the mechanical property is going to be enhanced, especially if it is in cold state, means we are deforming it at room temperature. Okay, it is also another advantage of this process is close tolerances is possible in this process, means there will be no much deviation in the dimension. So whatever the die opening dimension we have provided, almost exactly of same dimension we are going to get in our final product. Now, how to classify or how to divide this process? So broad classification is, it may be a direct extrusion process or it may be indirect extrusion process. So direct extrusion process means whatever the forces we are applying to deform the material and the material coming out, both will be in same direction. Just see here, this is the direction in which we are applying the force, and this is the outcome of the material, it is coming out in. So in both direction, if you will see, this both direction are in forward direction. If you are taking this one as x-axis, so both are moving in positive x direction. That is the one of the way through which we can differentiate or define this one. Another of course is there related to the friction and other things, but this is the one of the way through which we can define this one. So a metal billet is first loaded in a container. This is the container where this metal billet is loaded. Where is the metal billet? This is the metal billet which has been loaded over there, okay, or contained over there, having the die holes. You can see here, this is the die and it is having a opening or the hole over there. Okay, a ram compresses the material. Here is the ram which compress the material, means it applying the force so that it will go out, it will go inside that box, and through that it will pass through the opening provided over there, forcing it to flow through the die holes. That's what we discussed at the starting also. So direct extrusion, a significant amount of friction exists between the billet surface and the container walls. We can see here, this is the workpiece. This, if I will erase this one, so we can see here, this is the container wall, this is the container wall, and this is the workpiece. This is the container wall and this is the workpiece. This is the die opening and this is the die opening. So you can see here, the material is in contact with the container wall here at this point, this all point, and similarly material is in contact at this bottom part also in this container, and this part also, which is the die opening, material is in contact at this position also. So what is happening, once we are forcing through this ram, this material is flowing inside, so there is relative motion between this wall, because this is not moving relative to this one, this material is flowing and moving, so there is relative motion between this container wall and this workpiece. Because of that, friction is in this area, friction is in this area, similarly friction is in this area here also, this section or this section. So there is friction over there, that's what has been written. The amount of friction exists between the billet surface and the container wall. Billet is forced to slide towards the die opening. Because of the presence of friction, a substantial increase in the ram force is required. As there is friction over there, so obviously more force will be required to push this material to pass through the die opening. That had been written here. In direct extrusion, friction problem is increased by presence of, yes, obviously. We have already seen at the starting during the hot working and cold working. Whenever there is hot working deformation, I mean we are deforming the material at a high temperature, oxide formation or scale formation is very difficult to control. And once oxide will form, so this friction is again going to increase. So what will happen? There will be more pressure, ram pressure will be required to force the material to come out. So oxide layer on the surface of the, this oxide layer to cause defects in the extruded product. Obviously, if these particles, foreign particles will be there or oxides will be there, what will happen? As material is flowing over there, so chances is very high that it will be mixed over there and finally it will appear in the form of defect over there in the extruded products. In order to address the problem, yes. So how this problem can be reduced, this friction, or So what we generally do, as I told at the starting, what is the use of this one? This is known as dummy. This is dummy. There is no use of this one because this is the RAM through which we are applying the force. But between this workpiece and this has been provided. What is the purpose? First purpose is if we are applying force and these two will be in direct contact, what will happen? There will be some mark over there in this. Chances is very high that there will be mark over there. What is the another reason? The another reason, in order to address the problem, what is the problem? That friction problem. A dummy block is used between the RAM and the work billet. The diameter of the dummy block is kept slightly smaller than the billet diameter so that a thin layer of billet containing the oxide layer is left in the container, leaving the final product free of oxides. Yes, it's very important to understand. To overcome the oxide formation over there, this is the reason this dummy block is provided in between the billet, in between the workpiece and the RAM through which we are applying the force. Hollow sections like tube can be made using direct extrusion. So this is the main application. Even the hollow sections we can produce by this process. The starting billet is prepared with the hole parallel to its axis, yes, and the billet is compressed. The material flow through the gap between the mandrel and the mandrel will be also provided if we have to produce a hollow section through this process. Next is indirect extrusion. So indirect extrusion, one way I told how to how to define this process. You have to understand this one. The ram movement and the material which is after extrusion coming out, both will be in same direction. If it is direct extrusion, we can see here both are moving in positive x direction. But in indirect extrusion, we can see here both things are opposite to each other. If we are applying force in this direction, our ram movement is in this direction, means in positive x direction, the extruded product is coming towards me. It is in negative x direction. So if we are taking this one positive x and negative x, so what is happening? RAM is moving in positive direction, but after extrusion, that extruded product is coming towards the operator or it is coming in opposite direction. So this is one of the way through which we can define, yeah, we can tell what this indirect extrusion is. But beside this, other things are there which we'll see. In this type, the die is mounted to the RAM obviously and not on the container. This is very, very important. Here, the die is mounted on the RAM. It is not on the container. If you will see this one in direct extrusion, this die was mounted on this container. This is the container on which we have fixed the die. Here is the die. But in this case, in indirect extrusion, just see here, this die is mounted on the RAM. Die is mounted on the RAM. So here your RAM is, this hollow RAM is, and your die is mounted on that one. So just see here the die is. Here is the die. So this die is what we have done. We have mounted on the RAM instead of this container. This is the one of the difference, okay, and not on. As the RAM compresses the metal, as this RAM through that we are applying the force and we are compressing this one, it flows through the die hole on the RAM side, which is in opposite direction to the movement. That's what I told. It will be in opposite direction of the RAM. So once we are pushing this one, so this will be the direction of the RAM through which we are applying the force. And after flowing, once flow will start in the material, that extruded product will come towards you, means it will move in opposite direction. Since there is no relative motion between the billet and the container, this is the most important advantage of this process. As there is no relative motion, you can see here between the container and the billet, so there is no friction at the interface, and hence the ram force is lower than if we will compare with the direct extrusion. We have already seen in direct extrusion as there was friction between the billet or the workpiece and container. So because of that, ram pressure was more. But if we will compare here, there is no relative motion between the container and the billet, and hence there will be no friction between these two. And if friction is not there, so no need to tell. The forces that we need to deform the material or compress the material obviously will be less if we compare with the direct extrusion. What are the limitations of this one? Lower rigidity of the hollow ram, difficulty in supporting the extruded product at the exit. Yeah. This is the major difficulty with this process because of the low rigidity of the hollow ram. This ram is there because ram is not solid, no, now it is hollow, so its rigidity is less, so it will be very difficult to support the extruded product at the exit. This is the one of the major disadvantage of this process. Another disadvantage of this process is, as this process, the workpiece is coming towards the operator, whoever is applying the force. Suppose we are applying the force from this side and work extruded product is coming towards you, so handling of the material will be difficult. Means if we are doing a hot extrusion process, then handling of the material is going to be very difficult. Now we'll take one this numerical and we'll try to solve this one. How to solve this numerical, this drawing first we have to find out, okay? And then we'll stop this lecture here. So what this numerical reads, a 10 mm diameter steel wire is drawn through a die at a speed of 0.5 meter per second. So what is the diameter? Diameter is given 10 mm. This is the given 10 mm diameter. The speed is given 0.5 meter per second. So this value is given 0.5 meter per second. To reduce the diameter by 20%. Diameter we have to reduce by 20%. Okay. The yield stress of the material. So yield stress of the material means sigma y is given 800 megapascal. Okay. So what we have to calculate? We have to calculate power. So how to calculate power? Power can be calculated. How to calculate? Okay. So we already know power is nothing but force into velocity. We know this one. If there is linear movement or linear motion, we know power is nothing but force into velocity. And force is nothing but, we know, flow stress. If we are writing sigma because material is flowing, area into velocity, we can write this one. Okay. But the thing is, we don't know flow stress. Only in this problem, this 800 megapascal, the yield strength of the material is given. But there is a relation how to calculate. So first we'll calculate this flow stress. So this drawing stress sigma d is given as, this is not flow stress. This is actually drawing stress. Draw stress, so that it is being drawn. So sigma d, this is given as, there is a formula. This is given as this sigma d is equal to flow stress, that is sigma f, into what will be the value, this ln a naught upon a f, this final area. So this is given as this drawing stress is equal to flow stress into true strain. Okay, this is the formula through which we can calculate this drawing stress. So how to calculate this one? This ln a naught upon af we can write 2 times sigma f, and we can write this ln, and this we can write d naught upon df, means initial diameter and this final diameter. This 2, as this will be a square of this one, pi by 4 d square area, so it will comes out, and that's why we have written this 2. Now we have all the value, we can write the value here. So what will be this value? 2, and this value flow stress is given 800 megapascal into ln, and this value is also given. What this value is? Initial diameter is 10, and after this drawing it is reduced by 20%. So how much it is left? It is left means 8. Okay, so once you will calculate this one, this value will comes out 357 megapascal. This will comes out 357 megapascal. So now we have this drawing stress. This direct value will put here, so we can write 357 megapascal. What will be the area? Pi by 4 d square. D means 8. I into what is the velocity? 0.5 meter per second. This is megapascal, so no need to tell Newton per mm square. And here area also in mm square, so it will be cancelled out. So finally all these things will be in SI unit, so there will be no problem. Once you will calculate all this value, so finally it will comes out 8.97 kilowatt. So this is the final answer of this one. So what is important in this one? This formula is very easy. Everybody knows it. Force is equal to, sorry, power is equal to force into velocity. The important thing that we need to know is how to calculate this drawing stress, because directly this value is not given. Flow stress or yield stress almost same. It is given. So through that we need to calculate this one. Once you got this value, then after that directly we have to put here and we'll get the value. Okay. So we'll stop this lecture here. Next we'll come up with the another lecture based on this metal forming on some other processes. Thank you.